start. So, what was I saying? Yeah, so we're going backwards, basically. We're going from the masses of elements in a substance to the actual chemical formula. So last time we learned how to do that. We also learned how to use the actual molar mass of an entire compound along with that information to get not just the empirical formula, which was sort of the formula you can get from that process, but you're not sure it could be that times 2, times 3, whatever. But to get the actual molecular formula by comparing it to the actual mass per mole of a substance. There's actually one more thing I'd like to do along those lines, which is if you start without having the masses given. Right, so in last class I was saying, like, you have, 13.7 grams of hydrogen and 42 grams of oxygen. So, I don't know, something like that. Just making up numbers off my head. Then find the formula of whatever that compound is, right? But if you don't have that information, if you just have the percentages, so, 15% element A, 75% element B, at that point, you can still figure out an empirical formula. It just takes tiny bit more work. So, to that end, first of all, I'm going to start sharing my screen. I'll do a little whiteboard. And I need to make sure I have chat up. This always takes a time to set up. Sorry, everybody. Chat's up over here. Okay. So if we only have percent compositions, right? We don't have the specific amounts of a substance. We're only told the percents. We can still do this kind of problem. So I think the first one here I took from the textbook. It's an example in the textbook. So I'll read it. The bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of 27.29% carbon. So 27.29% carbon and 72.71% oxygen. Okay. And we need to figure out the empirical formula for this particular gas. So it's not so bad. We don't have an amount, right? We don't have total grams, so we can't do our steps that we had been doing before. But we have percents. So I guess the best way to put it about how I would approach this is I would make up a convenient number of grams for the total sample. Right? And if I make up 100 grams, say I'm saying whatever this molecule is, I have 100 grams of it. If 27.29% of 100 grams is carbon, how many grams of carbon is that? I mean, I chose 100 to make the math incredibly easy. What do you guys think it would be? (27.29% of 100). Oh dear, this is concerning. What does percent mean?
27.29
yeah.
grams.
Yeah, so 27.29% percent means per 100, right? So it's 27.29 out of 100. So if I just multiply by 100 grams, I'm going to get 27.29 grams of carbon. And likewise, 72.71 grams of oxygen. It's just the numbers given, right? That's why choosing 100 grams as your sample size is really easy. Just you can take the percentages then and just turn them straight into grams. No math needed, really. And then from here, we can go about our usual, what's it? Thingy. Our usual procedure, sorry. Which is, in other words, finding the number of moles, first of all, of these two substances. Oh, I'm sorry. And people had it in chat. I'm sorry. I didn't realize that. I don't know. Maybe I put chat over here so it's easier for me to see. Okay. So for carbon, that would be taking the 27.29 grams of carbon we have and dividing by the molar mass of carbon, which we've done many times before. 12.011 grams per mole. If you don't remember where to get this number, it is just looking at the periodic table. If you look at the mass, the atomic mass, usually it'd be given in AMU, atomic mass units, as 12.011. But since we know about the mole, we also know it's the same number of grams per mole for that same element. So this guy is it's going to be a little over 2, right? 27.29 over 12.011. 2.272 moles of carbon. Basically telling us how many actual atoms of carbon are in this thing. And then we're going to do the same process for oxygen, the 72.71 grams of oxygen, over its molar mass, 15.999. Again, another one we've seen a lot, grams per mole. 0.71 over 15.999. That, well, it rounds pretty inefficiently to 4.544659, so 545 moles of carbon. I'm going to keep the full precision number in my calculator for the next calculation. And of course, we're doing our little formula. Whoops, 272, sorry. And then we divide by whichever one of these is smaller. So we get to, well, obviously we're dividing by itself here, so just a single carbon. And then oxygen, I'm going to get the exact number here, divided by the exact number here. And I get 2.0002. I'm going to round that to 2. I think that's good. And we get CO2, which is an actual molecule we know. Despite the fact that we know that CO2 is a real molecule, this is still just the empirical formula. Right? It could be C2O4, it could be C3O6, or so on, any of those. In order to get the real formula, which I'm actually pretty positive is CO2 in this case, they're talking about bacteria fermenting, so I do know that a product of that is CO2, just from experience. It's the bubbles in soda, for example, or in a traditionally brewed soda, I suppose, not a normal soda these days. Yeah, that would be CO2. So it's almost certainly CO2, but we'd have to do an extra step in order to find that. Whoops. So, all of that being said, that is how you would go about doing this kind of calculation just from percents. It just adds this little extra step. You could choose any number of grams here to do this kind of conversion from percentages to grams. You could choose any number you want, but I think 100 is super easy just because it means you can just take the same number of percent and make it into grams, right? So I suggest that, very strongly, I suggest that. You will still get the right answer. If, for example, if I did like 27 grams here and I multiplied it out to get the correct numbers, whatever 27.29% of 27 is would be the number of grams of carbon, and whatever 72.71% of 27 total of oxygen would be the correct number of grams. I would get the same formula out here. I get CO2, but I just think choosing 100 here is way easy. So, all that being said, I promised you guys that this class we would be mostly focusing on practice problems. I also promised you that I would record the other class's lecture, which I did. I'm going to be posting that as soon as it uploads to YouTube onto Classroom. So look for that coming up. It takes a couple hours for YouTube to go through it. I don't know what's up with that. Also, at the end of class today, I'm going to assign you guys a new homework on this subject. But before we get to any of that, I'd like you guys to do a bunch of practice work. So, first practice problem. Oh dear, I just opened the wrong thing. Where are my practice problems? Here they are. The first practice problem asks for what is the empirical formula, so just like the process we did above, of a compound containing 40% carbon, 40.0 I should say, 6.71% hydrogen, and 53.28% oxygen. So go ahead and work on this. I'm going to give you guys... I'll check in after 10 minutes and see how it's going. This is exactly the same process as we just did above, up here. So I'll leave it up so you can look at what we did. And get to whatever empirical formula you can figure out. Okay? If you get an answer, type it out to me in chat, and I'll monitor that. This is kind of the same as this one above, right? We're starting in percentage composition, not actual number of grams of this substance. So, again, I'm just going to choose 100 grams as the total mass for my sample because it makes the math way easier, which means I have 40.0 grams of carbon, 6.71 grams of hydrogen, and 53.28 grams of oxygen. And then I want to convert these numbers of grams into moles of the substance. Right? So I have an amount, a mass. Now, I do want to make absolutely clear. The textbook and some chemistry places call it a weight of this particular thing. This is not a weight, actually. It's a mass. It's a very subtle and kind of dumb distinction in this case. It doesn't really matter. But just in case any of you want to take my Physics 1 class next year, just in case, mass and weight are very different things. And I don't know. It's one of my things. I'm sorry. I'm just on my soapbox. I'll get off of it now. And we'll keep going with this. So we want to convert these masses to just numbers. Oh, weight is not mass. Weight is not mass. Weight is caused by mass, but it is not mass itself. So I want to take these masses and convert them to an actual number of atoms, which is moles, right? Moles is telling us how many atoms there actually are here. So 40.0 grams of carbon divided by carbon's mass per mole. What is that? I need to look at 12. Oh, it's right there. 12.011. It's literally right up here. 12.011 grams per mole. And where's my calculator? 40 over 12.011 gets me to 3.330 moles of carbon. I'm going to draw arrows just so I can Weight is mass times gravitational pull. That's, well, gravitational acceleration. Yes. Yes, that's exactly right. Absolutely. In fact, it's what we're literally covering right now in Physics 1, which will be third block today. So 6.71 grams of hydrogen divided by hydrogen's molar mass, and I just remember this one, 1.008 grams per mole. I should remember carbon because I've used it so many damn times. This is going to be pretty close to 6. 6.71 divided by 1.008. 6.6567, so 6.657 moles of hydrogen. And then for oxygen, 53.28 grams of oxygen. And oxygen's molar mass is that 15.999 grams per mole that we saw before. So what is this going to be? It's going to be a little bit less than 4, I'm going to guess. 3.33 again. It's like the same number as above. So we're going to have carbon to 3.33, hydrogen 6.6567, and so on, and oxygen 3.33. Then we divide by our 3.33, right? The smallest one of these numbers here. Divide everything by it. Just so it's very nice that carbon and oxygen have exactly the same numbers here. So these are both going to be 1s, right? Carbon and oxygen here, 1s. And then this hydrogen, we need to figure out what it is. So I'm going to go into my calculator, grab that number, and divide by our 3.33. It's 1.9988978. It's 2, right? We have a CH2O. And that is what I believe everyone had for the answers I saw. And that is, in fact, the right answer. Beautifully done, everybody. Now, that's the empirical formula still. We don't know. It could be some other formula. If I look at my P table really quick. C, H, and O. Oh, that could be formaldehyde. Yeah, I think that's CH2O. Oh, yeah. Cool. That's a dangerous chemical. It's a preservative. Interesting. So yeah, that could be formaldehyde. Okay, so I have a couple more sample problems for you guys to do. So let me start a new color, and let's try them. They're basically the same as the ones we've done. In fact, this first one is actually straight from the textbooks as well, because I kind of liked it. So it's we're looking at nicotine, which stuff that's in cigarette, responsible for the addictive nature of cigarettes is what the book says. Nicotine contains 74.02% carbon, 8.710% hydrogen, and then 17.27% nitrogen. And then it gives us a little bit of extra information. Well, first of all, let's find the empirical formula just from this data. And then I'll give you the extra information. We can find the exact formula. So yeah, let's just do this problem, basically the same problem over again with these elements. And I have some of the extra information for you. Again, I'll give you, it seems like you didn't take all of the 10 minutes I wanted to give you, but let's try like 5 minutes now, maybe? I'll try 11:10. How about that? So again, we're assuming there's 100 grams total of whatever this substance is, so that our amounts are 74.02 grams of carbon, 8.710 grams of hydrogen, and 17.27 grams of nitrogen. That's the easy part, right? Then we do this same darn process of converting all these to number of moles. Just like before, for carbon, we know that number. What does that work out to be? It's going to be like 6. Whoop, I need my... 6.163 moles of carbon there. For hydrogen, 8.710 over 1.008 grams per mole. It's going to give us 8.710 divided by 1.008. 8.641 if I round. And then what did we have here? It was 17.27 grams nitrogen. Divide by... Oh, I need to find the molar mass of nitrogen. I don't remember that off the top of my head. 15.099. Is that right? No. No. Haha! 14.007. I need to be looking at the right tab on P-table. That sounds more right. 1.233, really? Then we do a little formula. And we divide by the smallest one of these three numbers here, which is the 1.233. I'll do that in my calculator here. So we get, when I divide by the 1.233 for hydrogen, I get 7.008. That's close enough that I'm going to round it to 7. Nitrogen obviously becomes a 1. And carbon, when I do that division, hold on, I need to scroll up to find that number. Divided by 1.233. I get 4.998. That's 5 if I round. So C5, H7, N1, I suppose, technically. That is our empirical formula. But we actually have a tiny bit of extra information. We know, or the textbook gives us anyway, a little bit of extra information that this substance also, it says 40.57 grams of nicotine contains 0.2500 moles. So we can actually find the number of grams per mole by just doing this division, right? 40.57 grams over 0.25 moles is going to give us the number of grams per mole. Basically the same as multiplying by 4. 162.28 grams per mole. The way we can use this, and we haven't practiced this a ton, so I'm going to just run us through it instead of setting you loose on it right away. The way we can use this is we can compare this number of grams per mole to the number of grams per mole of what this empirical formula would be. If they're the same, then we have the right formula. If they're different, then we can do an extra step to find out what the actual molecular formula is. So let's go through and actually find the molar mass of this formula here. We have our little tables. I hope you guys remember from a little while ago. Carbon, hydrogen, and nitrogen. I'll do my separate rows here. The mass of each, in AMU anyway, 1.008 and 14.007. The number of each in this molecule, there are 5 carbons we just found, 7 hydrogens, and 1 nitrogen. And then based on all those, the total mass. So 5 times 12.011. I'll plug it in. 60.055. 1.008 times 7. 7.056. If I had thought about that for more than half a second, I would have been able to get that number in my head quicker. And 14.007 times 1 is 14.007. Then we're just going to add these 3 up. And our total molar mass for whatever this formula is 80, not 8 point, not even 80, it's 81.118 AMU. So 1 molecule of this substance, of this formula anyway, would have a mass of 81.118 AMU. A mole of this substance would have a mass of 81.118 grams. So this substance is 81.118 grams per mole, which we'll note is different than this guy over here. Than this guy here, right? So what we need to do is we need to take the grams per mole of the actual substance and divide by the grams per mole of the formula we found. So our 162.28 and divide by the 81.118 to get some number. Let me find the exact precise numbers in my calculator and do this division. Oh, and this number turns out to be 2.000 54242, whatever. It's 2, right? What that tells us is that in order to get to the true formula for this substance, we multiply all the numbers in this formula, our empirical formula, by 2. So C times 2, C5 times 2 would be C10. 7 times 2 would be H14. And N, nitrogen, there's one of them, times 2 would be 2. So this gives us the true formula for nicotine. Okay. A pretty complicated process, right, guys? We got 10 minutes left. Let's do one last one. Let's do just one last problem. Everyone done writing this down so I can go to a new page and start us on a new problem? Okay, I'm going to start a new page. Last problem for the day. Okay. We have some mystery compound that is 49.47% carbon, 5.201% hydrogen, 28.84%, whoops, my percent got a little weird there, percent nitrogen, and 16.48% oxygen. It also has a molar mass for the entire compound of 194.2 AMU. So, from this information, figure out what the formula is. I'll give you guys, well, we don't have much time. Do your best in 5 minutes. We'll see if anyone can get there. Okay, we are really limited on time remaining, so I know pretty much no one's had a chance to actually solve the whole thing. but I think we should go through it just as practice. So let's do it really fast, like real fast. Okay. Assuming there's 100 grams of my substance, grams carbon. Yes, Ella, that is it. That is perfect for the empirical formula. So the moles of carbon in a 100-gram sample would be 4.119, I suppose. I should color code all these. That would be nice, wouldn't it? Oh well, it's going to take too long. (5.201 grams of hydrogen divided by its molar mass, 1.008 grams per mole, gives us 1.1597. Not a good thing to round. Moles of hydrogen. For nitrogen, 28.84 grams of nitrogen over its molar mass of 14.007 grams per mole. 28.84 over 14.007. 2.059. And then, what have I got here? Not that one. This one. 16.48 grams of oxygen. Sorry. This would be a 5.159 on a 1.159. Divided by oxygen's molar mass of 15.999 grams per mole. Maybe just over 1.030 moles of oxygen. I should be complete. So we have there's our ratios anyway. If we're looking for the formula. Oh, and Michael, that I think that's right. You always put it in a different order than I have, so it's harder to look at. We divide by the smallest one. We'll do carbon first. I get 3.9985. That's 4. Then hydrogen divided by my 1.030. 5.009. That's a 5. Not so bad. Nitrogen, my 2.059 divided by my 1.0030. I get a 1.9987. That's a 2. And then oxygen is a 1. So there is my empirical formula. And Julia, I think you've got it exactly right there for the whole molecular formula. Michael, is that what you had? I think it's like exactly backwards of what I had, but yes, I think you're right. Just in the reverse order. And then to find the true formula, right? We need to do this thing with the mass again. Carbon, hydrogen, nitrogen, oxygen. Doop, doop, doop. We know all these, mass and AMU. Gwen. I think it's a little big. I think that's twice what it ought to be. I had how many? I had 4 carbons, 5 hydrogens, 2 nitrogens, 1 oxygen. So 14.007 times 2 would be 28. That's the worst 8 I've ever drawn in my life. 28.014. What's 8 times 5? I forget. 50 minus 16. So 34. I think that's right. I might be wrong about that. Honestly, I should actually check that. 5.04. Yeah, I was wrong. Just cross that out. 5.04. And then 12.011 times 4. Something 0.044. 48.044. Adding these together. 28.014 plus 15.999. I'm getting 97.097. If I divide these, I get 2.00006. That's 2. So we're multiplying our formula here by 2. I guess technically the way to write that out would be doing the empirical formula and then in parentheses and then doing the 2 outside the parentheses like as a subscript. That tells us we're multiplying all of them by 2. Whoops. I'm a lemming. I just started copying what I see instead of writing it down. There's our formula. And we are well past the end of class. I apologize, guys. I want to let you know that there is a homework due a week from right now, or I guess a week from the start of class on Thursday. It's 3 problems covering this kind of stuff. So yeah, if everyone could at least try the problems by Monday. So if you have questions, we can go over them. That would be amazing. And heck, if you finish it and there's no problems, then you're done with your homework. Yeah, so that's that. It's up on Classroom right now. Homework 4, I think it's called. That's at least what I called it. Yeah. Can I add these notes to Classroom? Yes. So I will add these notes to Classroom, the ones from last time, and I'll get that video and probably, hopefully, cross your fingers, this video up. The videos take longer to upload. It just takes a long time to do it. But these are pretty easy to do. So I will get that at least by the weekend. Sound good, everybody? All right. Take care, everyone. Have a good weekend, and I will see you on Monday.